Hello everyone, welcome back to the online tutorial on quantum chemistry. We are going through the early stage development of quantum mechanics, where we found the simplest construction of an atom by Niels Bohr. In that atom model, electron is a subatomic particle which revolves around the nucleus in certain well-defined circular orbits. We found that Bohr model faced several failures despite its great success to explain the emission spectrum of hydrogen. So Bohr model gives only a partial insight into the electronic structure of atom. A major breakthrough in our understanding of the electronic structure of atom and also in the entire concept of the early quantum mechanics was put forward by a French scientist called Louis de Broglie, and he put forward an important concept regarding the nature of matter. De Broglie said that matter has two natures. Matter behaves like waves and matter can behave like particle. And this is called the dual nature of matter. Dual nature of matter. Or the de Broglie's concept of matter waves. It was in 1924 Louis de Broglie put forward this concept in 1924, and even before that the dual nature of light was known. Light at times behaves like waves and certain other times light behaves like particles. For example, when white light is passed through a prism, it is dispersed into its individual colors and you can get a spectrum. And this is due to the wave nature of light. And in another example, when light is directed to a metal surface, this is a metal surface, and light is directed to this metal surface, and if this light has certain threshold frequency, then electrons will be ejected. And this is called the photoelectric effect. And this photoelectric effect was explained on the basis of particle nature of light. And these particles were termed as photons. Albert Einstein, from his famous relativity theory, put forward an equation which relates the momentum of the photon, that is P, which is equal to h divided by lambda, where lambda is the wavelength of the light. And Louis de Broglie suggested that if light can behave like both particle and wave, matter can also behave like both particle and waves. And not only that, and such matter which behaves like wave and particles also obeys a similar equation. For example, if the mass of a body is m and if it travels with a velocity v, then momentum of that is equal to m times v. And in that case, the wavelength associated with this matter, lambda, is equal to h divided by p, or lambda is equal to h divided by mv. So matter has both wave nature and particle nature. Does that sound illogical? Does that make any sense? Is there any problem to understand this? Yes, there is a problem to understand this. The problem is because we always compare the unfamiliar things with the familiar ones. For example, we always compare an atom or an electron with a billiard ball or a tennis ball or a cricket ball. And we compare the light waves with the water waves. Why do we compare like this? Because we haven't seen the atoms. With the naked eyes, we cannot see the atoms. So we compare the atoms with something that we are familiar with. Billiard ball is a familiar one, so we compare the atoms with billiard balls. This is just because of certain prominent features between them. For example, atoms when they collide each other, they can bounce apart. Billiard balls also, when they collide each other, they can also bounce apart. Atoms or billiard balls, when they are thrown against a certain surface, it can exert a force on that surface. Atoms are also like that. When atoms are hitting a surface, the atoms will exert a force on that surface. For example, an umbrella in the windy season. The wind is nothing but the flow of molecules in the air. Molecules are the small combinations of atoms. And when then these molecules hit the umbrella, these molecules exert a force on that umbrella that we can feel in our hand. That's why we struggle to hold the umbrella in the wind. But there are huge differences between the atoms and the billiard balls. For example, atoms with a certain threshold energy, when they collide, they can make a bond between them. But that doesn't happen in the case of the billiard balls. Billiard balls, when they hit each other, they don't make a bond between them. And also in the case of size, billiard balls, we can see, we can touch, we can take it and we can throw it against something, but that is not the case of atoms. We can't see atoms. They are so small compared to the billiard balls. Similar is the case with the comparison of the water waves and light waves. We know the light, but we haven't seen the light waves. We don't know how the light looks like inside. So we compare the light waves with some other waves that we are familiar with. That familiar wave is the water wave. When we put a stone on the surface of the water, it makes water waves. So we compare the light waves with the familiar water waves. Water waves and the light waves, both of them are characterized by crust and troughs, or the amplitude, wavelength, frequency, etc. And so they are similar. So certain prominent features of the light waves and water waves are similar. That's why we compare the light waves with water waves. But light waves and water waves are very much different as well. For example, in the visible range, light waves makes the feeling of vision in our eyes, but sound waves never makes the sense of vision in our eyes. Or light waves can pass through water, light waves can pass through air, light waves can pass through vacuum, it can pass through certain solid, but that's not the case with water waves. Water waves are called wet waves. They exist always on the surface of the water. So they are different as well. Still we compare the light waves with the familiar water waves because of certain prominent features between them. But sometimes this comparison is dangerous. We cannot always compare an atom or an electron with a billiard ball. A billiard ball is a particle or a wave. In fact, we will give a sudden answer that billiard ball is a particle. It has particle nature. But the correct answer is that it has both nature. It has particle nature and wave nature. But in fact, the particle nature is very prominent compared to the wave nature. The particle nature is observable, but the wave nature is undetectable. So we often come to a conclusion that every object like billiard ball, cricket ball, tennis ball, football, me, you, every one of us, we all have the particle nature. In fact, we have a wave nature as well, but our wave nature is so obscure that we cannot detect it. So when we compare a billiard ball with an electron, it's a dangerous comparison when we realize that electron has not only the particle nature, it has a prominent wave nature as well. To understand how observing only the prominent features lead to illogical conclusions, let us consider an example. Consider a cylinder. If the cylinder is held vertically, it appears like as a rectangle. The cylinder is held vertically in front of the eyes. Then it appears like a rectangle. And it can be moved in such a way that it will pass through a rectangular hole. And if the cylinder is held horizontally, it appears like a circle, and it can be moved in such a way that it will pass through a circular hole. Suppose one person sees the first scene and another person comes and see the second scene, and they come together and they start arguing. The first person says that it's nothing but a rectangle, because he found that it is passing through a rectangular hole. The second person says that no, it was a circle, because he found that it was perfectly passing through a circular hole. Both of them will argue, and the argument will never reach anywhere. But we know that it is neither rectangle nor the circle. But we know that the cylinder has a rectangular property, because the cylinder has a rectangular cross-section. And we also know that cylinder has a circular property, because the cylinder has a circular cross-section. Neither the circle alone nor the rectangle alone defines the cylinder. The complete cylinder can be defined on the basis of both properties, that is the rectangular property and the circular property. We know this. But if we say this to the first person, that we say him, no, it has not only the rectangular property, it has a circular property also, he will be outraged. He will say, no, how is it possible? How the same thing can have the rectangular property and circular property at the same time? How come a rectangle can be a circle? And if we say this to the second person, that it has not only the circular property but also the rectangular property, he will also be outraged. He will also say, no, it is not possible, the circle cannot be a rectangle, I saw this. Actually, both of them have partial insight. But we know that it has both rectangular property and circular property, and both these properties completely define the entire cylinder. The same is the case with matter. When someone says that matter has both wave nature and particle nature, we cannot argue that it is wrong based on a partial insight into certain prominent features. At least for the scientist, it makes sense. At a certain time, the particle nature will be prominent, and in some other time, the wave nature will be prominent. Or for some objects, the particle nature will be so large and the wave nature will be so upscale. So we have to understand that the matter has both wave nature and particle nature, but there will be an imbalance. In most of the familiar objects or familiar things we know, or in the macroscopic world, this imbalance is very, very high. For the macroscopic objects, the particle nature is so prominent and the wave nature is so negligible. But that is not the case in the microscopic world. For example, in the case of an electron, the particle nature and the wave nature both are prominent. At certain times, it will behave like a particle, and at certain other times, it will behave like a wave. That depends on what we are looking for. Now let's try to calculate the wavelength of a cricket ball and also the wavelength of an electron. You know that the mass of a cricket ball is something like 157 gram, and it's a fast ball, so its speed or velocity is equal to 42 meter per second. The de Broglie's wavelength lambda is equal to h divided by mv. That is equal to 6.626 times 10 raised to minus 34 kilogram meter square second raised to minus 1 divided by mass is equal to 157 gram times velocity is 42 meter per second. And this is equal to 1 times 10 raised to minus 34 meter. This is a wavelength associated with the cricket ball. And for simplicity, let me try to write it like 10 raised to minus 12 divided by 10 raised to 22. Why I wrote like 10 raised to minus 12? Because in the familiar electromagnetic spectrum, we know that gamma rays, they have the shortest wavelength, that is of the order 10 raised to minus 12 meter. Then comes X-rays, they have a wavelength of the order 10 raised to minus 10 meter. And then comes UV rays, then visible rays, then IR, then microwaves, and then radio waves. And with this familiar electromagnetic spectrum, gamma rays have the shortest wavelength, 10 raised to minus 12 meter. And that's why I wrote 10 raised to minus 12 divided by 10 raised to 22 here. So we can write like a wavelength of gamma ray divided by 10 to the power 22. It's a big number. 1 followed by 22 zeros. 1, 1, 2, 3, 4, 5, 6, 7, 8, 9, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22. So this is a ridiculously small number. The wavelength or the shortest wavelength corresponding to the gamma rays divided by a big number. So this is a ridiculously small number. Ridiculous. That's the best word to explain it. So the wavelength of a cricket ball is so negligible that we cannot detect it. It is so small, and the particle nature is the prominent feature in the case of the cricket ball. But what about the electron? Electron has the mass 9.11 times 10 raised to minus 31 kilogram, and let's suppose that the electron travels with a speed of 1% of the speed of light. The speed of light is equal to 3.00 times 10 raised to 8 meter per second. So 1% of that is times 1 divided by 100. So the wavelength, the velocity of the electron is 3 times 10 raised to 6 meter per second. And let's try to calculate the wavelength of this electron. And the wavelength lambda is equal to h divided by mv, that is equal to 6.626 times 10 raised to minus 34 kilogram meter square second raised to minus 1 divided by m times v. M is 9.11 times 10 raised to minus 31 kilogram times v is 3 times 10 raised to 6 meter per second. And the answer is 2.41 times 10 raised to minus 10 meter. See, this is in the order of 10 raised to minus 10 meter, and 10 raised to minus 10 meter corresponds to the X-rays, that is in the detectable range. So the wavelength associated with an electron is in the detectable range. It is not like the wavelength of the cricket ball. So here the wave nature is very prominent. So what do we understand from this? Cricket ball is in the macroscopic world, but the electron is in the microscopic world. So in the case of an object in the macroscopic world, the wavelength is not prominent and the particle nature is the prominent one. But in the case of an electron, the wave nature is prominent. So de Broglie's concept of matter wave has a great significance in the microscopic world. Now we are in a turning point. So far we thought like electron is a particle, but now we understand that electron is not only a particle but it has wave nature as well. In Bohr model we thought like electron is a particle which revolves around the nucleus in circular orbit. And now we have to consider that electron is a wave as well. And so we will try to fit this electron wave inside the Bohr model. Suppose this is the Bohr orbit and an electron wave exists in this orbit. And we will construct an electron wave from here. See, this is the crust and this is the trough. So this constitutes a wavelength, and again comes crust and trough, and this is the second wavelength, this is first wavelength, this is second wavelength, and again comes crust and trough. This is the third wavelength, and again comes crust and then trough, and then it meets the original position, that is the fourth wavelength. In this way it constructively fit inside the Bohr orbit, so it's fine. Now let's consider another case. So the wave we start to draw from here. This is one wavelength. Second, third, fourth, fifth, sixth, seventh, eighth, ninth, 10th. See, in this case, the 10th wavelength reach here. So, when we reach the original position where we start from here, it is only 9.5 wavelength. 9.5 wavelength. And when it is 9.5 wavelength, the crust of the first wave and this trough of the last one, they come together so that they destructively interfere, so that the electronic wave will perish. It will not exist. So what do we understand from this? In order to fit the waves inside the Bohr orbit, the condition is that the circumference of this circle, or 2 pi r, should be equal to an integral multiple of the wavelength, or n lambda. If it is an integral multiple, it will constructively fit inside the Bohr orbit. But if it is not an integer, if it is like 3.7 or 9.5 or 2.3 or any other, if it is like that, then it will not be constructively fitting inside the Bohr orbit. And from the de Broglie's concept, we know that lambda is equal to h divided by mv. So 2 pi r is equal to n times h divided by mv. Or we can write mvr is equal to n h divided by 2 pi. Have you seen this equation anywhere else? Yes, we saw this in the postulates of Bohr model. This is the angular momentum of the electron, mvr. mvr is an integral multiple of h divided by 2 pi. This was the famous postulate of Bohr, the angular momentum quantization. So we reached that the same equation by trying to fit the electron wave inside the Bohr orbit. So the electron wave, the consideration of electron wave gives a physical interpretation of why the angular momentum is quantized in the Bohr orbit. It was in 1924 de Broglie put forward his famous concept of matter waves. And 2 years later, it was proven experimentally by G.P. Thomson. For that, G.P. Thomson directed a beam of electrons to a thin gold metal foil. And when these electron beams passes through the thin gold metal foil, it gives diffraction pattern. It was known at that time when X-rays passes through the metal foil, thin metal foil, it gives diffraction pattern. In the same way, electrons also after passing through the metal foil gave the diffraction pattern. It means that electrons behave like X-rays or electrons behave like waves. For his theoretical contribution of the matter waves, de Broglie was awarded the Nobel Prize in Physics in 1929. And for the experimental proof of that is, for experimentally proving that electron is a wave as well, G.P. Thomson was awarded the Nobel Prize in 1937. Remember that this G.P. Thomson was the son of that father J.J. Thomson who discovered electron as a subatomic particle. And father also got the Nobel Prize for discovering electron as a subatomic particle. So now we have come to a turning point. Electron is no more a particle alone. Electron is a wave as well. This had serious consequences in the later development of quantum mechanics, and such things we will learn later on.